Okay, welcome to the CMake session. This is a shared session between Lukas, who is in the back, and myself. I'm Hannes. And half of this training actually is about CMake, so we have 4 sessions. And in each session we will have some theory, a presentation, introduction, and hands-on part where you can work on some examples and write the CMake for it. You can interrupt me at any time. Please ask if you have questions.
Lunch is flexible too, with sandwiches.
Okay. And we will be teaching so-called modern CMake at some point. And modern means it's evolving, and maybe we are also not up to date on all the best practices for the most recent version. So if you know more than we do, please correct us. But yeah, so for our background, let's say I'm using CMake probably, I don't know exactly, definitely more than 5 years. But I think I learned it only maybe a year ago when we worked on our project and wanted to make it public and easily usable by others. And so we started to learn how to do proper CMake. And we will explain later what proper CMake is and how you can write a bad CMake. You will see as well. So yeah, here's some material that you can have an additional look at. Some of the stuff there you will see also in our presentation. But most of it is just taken from CMake.org, the official site and documentation. So the 4 sessions will be first about CMake Basics, because I think a lot of you don't use CMake at all so far. Then in the next session we will talk particularly about what is modern CMake. And in the 3rd session we will explain how you make your code available by exporting your library as packages. And the 4th session is about best practices and some advanced topics, more like individual self-contained small bits. And here I could borrow some time to John if you want to learn more about Git than about modern about advanced CMake. So we did a small survey by email before the course just to understand how much you know already about CMake. And maybe we can do another survey here. Just raise your hand if you already worked with CMake in your own projects. Who worked with CMake? So it's just 5-6 people. So all the rest did not use CMake at all. I mean, for your own project. Okay. So what else are you doing? Are you using Makefiles? Raise your hand for Makefiles. Okay. What else are you using? Well, first, a different question. What languages do you use? CMake is mainly about C++, maybe also about Fortran, but it's only relevant for compiled languages. So who is using C++? Who is using Fortran? Who is using Python? Who is using something else?
Objective-C.
Okay. I have no idea if it's covered, probably with CMake, yes? Yes?
I'm using Makefiles.
Okay, so if you're using Makefiles, then probably you want to use CMake, if it has good support for Objective-C.
Who knows?
Okay, do I have other questions? I think that's it. Of these 5 people who use CMake, who is using modern CMake? Do you know what it is? Okay. Okay, good. So when we started, actually we expected that we will teach mainly modern CMake, but apparently we are teaching mainly CMake Basics. So we start from nothing, and in hands-on you get experience with it. So CMake Basics. First, I will motivate why you should use CMake, or why it makes sense to use CMake. Then we learn the basic commands, how you use variables, targets. Your targets are your libraries or your executables. How the CMake build process works. Functions are already a bit more advanced, but very helpful. And then how you use external libraries, packages, and how you install your library in a very basic way. This is for today, or not for today, for this session. And in the hands-on, you will apply all these things. So what is CMake? This is taken from the official website. CMake is an open source cross-platform family of tools designed to build, test, and package software. So the main thing is building, and the tool for this is the CMake itself. It has an additional tool called CTest for testing. It also has a tool called CPack for packaging. But we will not cover CPack. We will probably cover CTest a bit. And the main thing, it's a cross-platform tool, and it already does a lot of these cross-platform complications for you. So if you use different compilers, it already knows the proper flags for some of the stuff, and that's where it gets helpful. So actually, CMake is not a build system on its own, but it's a build system generator. So if you run CMake, you tell it, please give me make files, and will produce make files for you. It's a bit similar to the auto tools that you maybe also know. Who knows auto tools? Okay, I've never used it. I know they exist. CMake is quite old already. It's from 2000, so 19 years old. But it became much more usable in about 2014 with version 3.0, which is referred to as modern CMake. And you will learn what it is. Now, why should you actually use it? I think it's fair to say that CMake is a de facto standard for building C++. If you look on new projects, you will most likely see that they are using CMake. And many big projects are using CMake as well. For example, LLVM changed to CMake quite recently. I don't know exactly when. Boost has a plan to move to CMake, even if they had for a long time their own build system. And if you look at Google Trend here, I compare here CMake, AutoConf, and Bazel. Bazel is a build tool from Google, and probably also City, because I think starting from here, the tool was released, so all the rest is just noise from the City. And what you can clearly see is that the AutoConf was very much used in 2004 and I don't know, until 2010 maybe, and then CMake just started to take over. And so, yeah, it has some limitations, or there are some people who hate CMake, but everybody's using it anyway. And especially in the most recent version, it got so much better, and it's now, I think, quite nice to use. So most of you know makefiles. This is a basic makefile to compile my example, and makefile experts maybe have comments and say, this is not a nice makefile. I don't know, because I did not write makefiles for many years. But what you can see here is usually you have to, so let's say everything is explicit. So you have to do a lot of work if you want to support different compilers and so on. Here it's just hard-coded. And if you want to have a clean target, you have to provide it manually and so on. If you compare this to a simple CMake script doing the same thing, it's actually just one line with 2 lines of boilerplate at the top. So what you always do when you write a CMake file, you say, I have a minimum required version. You should just put it. And then you specify you have a project with a name. and the languages that you will be using in this project. And then you just say, give me an executable with the name myExample, and the source is example.cpp, and there you go, you get this build by the commands that you see here. Usually what you do is you create a subdirectory, often called build. From there you call CMake ... pointing to the folder below, where the CMake file, the starting point is. And then you just say CMake ---- build dot. And this is calling, this last step is calling actually make if you use the make file generator. Because the CMake doesn't only support just generating make files, but also other things. Like, for example, Ninja, or it also can generate files to be used in IDEs. For example, you can generate Visual Studio project file and so on. Okay, so many of you did not use CMake at all, so let's have a quick look how it works. So you cannot see it because it's here. So I made a small example which has a C++ file which just prints hello world. And I have a CMake file which has the minimum required version, the project name, an option that I will show later, and then this add executable. Now I do make the build, cd build, CMake ... and then you get some output. You already see here, you don't have to specify your C++ compiler explicitly. It tries to find one. In this case, it found my GCC 7.3, checks that it works by compiling a minimal example. And in the end, it says configuration is done, generation is done, and now my build files are in this directory. So from there, I can just call make, and it will build my example, and I can execute it. Okay, this is what CMake can do. And now, as a starting point, before we come to the maybe a bit try part where I explain all the commands that you need, another example, a bit more advanced. So the first two lines, you know them already. Then there's a new thing, find package. This is if you have a dependency on another library. For example, in this case, it's a dependency on OpenMP. I say find package OpenMP, and it will try to find it for me. We will come to how it will try to find it later. I also say that this is required. So if it cannot find OpenMP, it will just give an error and abort at this point. In the simple example, I just had an executable. Now I also build a library. I say add library, my library. I put the source file in, and then I link my library with OpenMP. Apparently, it is using OpenMP. And in the next step, I make another executable where I'm using this library that I just created. So with this, I can create some dependencies between my files, between internal libraries and external libraries. Any questions so far? Okay, now we need to start with the CMake Basics. So there's mainly three kinds of CMake files. We don't cover the second one, so I will just talk about the first and the second, the first and third. So the main thing you write is a file is always called CMake lists.txt. So this is your starting point for your project. It's in the root folder of your project usually. And when you type CMake ... you actually were referring to that file. And then, if you have subdirectories, usually you include other CMake lists.txt, which are in your subfolders for example, in the source subfolder and so on. And this is the first thing that's a bit annoying with CMake is that in the end you will have 10 files open in your editor, all called CMake lists.txt. It's quite hard to find them. Now, CMake syntax is quite simple. Everything is a command. So all the syntax is command, opening parenthesis, something, closing parenthesis. Okay, so not everything, there's also comments. And then you can have keywords in this command. They're usually uppercase, but this is not a requirement. Sometimes CMake is case sensitive, sometimes not, also a bit annoying. The other simplification in CMake syntax is everything is a string, so there are no different types. So, for example, if you create a variable, let's start from the lower one. I have a pointer here. Here, for example, I have a variable called from, and I set it to the string from. Other things that you can do with variables is here you can, so with the $, you're expanding the variable. It's a bit like bash. So for example, here I set the other var to the result of my var. This actually is defined here and set to an environment variable. And you can also reference cache variables. I come to that later. What you can also do, you can nest variables in variables. So what you do here, you expand, the variables are expanded from inside out. So from is set to from. So from here expands to from. And then you expand the from cache, which is this variable. And this is a command to print a message. And so this is a collection of things that you will later need in your hands-on. So this is not working because I didn't connect it. There's another complication regarding variables and strings. So sometimes strings are interpreted as lists. So lists are just strings separated by semicolons. So in this example here, I create a list with 2 entries, first and second. I can append things to that list, and I'll skip over this next thing. Okay, no. You have another list command. We can say join my list. So you join all the entries with this separator, and you get another list. This time it's not a list, it's a string, because it's not the semicolon separated string, but colon separated string, so it's not a list, but what you get here is this output. Then, like in other programming languages, you have control flow operations. For example, you can iterate over a list for each element in this list. You can do something. You can have an if on this variable. So what it's doing here is, for each element in this list, which are all these letters, a letter is assigned in each iteration with one element. Then here you check if this letter is not in the second list, you will print something. And then if and for each has many variants. So for what you can actually pass in here or pass in here. And here are links in the slides to the documentation. And you probably have to look it up yourself and try yourself, because if I explain all these variants, this is probably already the first session. And I should connect this thing because I'm always using it. Okay, you already saw a first CMake list.txt, an example. And I already explained that you need this CMake minimum required version. This is just to tell CMake which CMake version you require, because older versions don't have all the features that you need, maybe. And we are using in this hands-on session the latest CMake version, which is 3.14. It's a quite easy dependency, so it's easy to install CMake with the latest version. That's why I think you should not care much about people not having the latest version. Just tell them, install the latest version. It's an easy dependency. And with latest versions, there came so many new features that it's usually worth it. The next thing is project. I already explained it. You give it a name. You can give it a version number, which we will use in some later exercise. And you can specify languages. For example, CXX for C++, C, Fortran, CUDA is also a language in CMake. This is already a bit special. If you want to enable a language only for parts of your project, then you can do it with enable language at some level. No, actually, I remember that we had a discussion on this, and here it's written. So actually, you should enable it on the top level CMake. I think it works if you do it for sub parts, but there could be problems. So actually, it's just an alternative to put it directly here. We have examples when you want to do it in this way. Then a command that you also will use frequently is add subdirectory. I already mentioned this. You have the top level CMake list, then you have some sources, and you usually don't want to refer to all the sources in the subdirectories from the top level CMake, but you want to modularize it. So if you have a source directory, you put another CMake list into this source directory, and then you deal just with the files locally in this directory. And then there's the last thing here is you can include other files. This is a bit like in C++, including a header. And actually, I skipped over this thing here. So these include files are usually called something.cmake.
You mentioned subdirectories there, allow create a recursive project. So frequently I download projects and then I put them into subdirectories of my existing projects and then just go add. And then you want projects which are projects in their own right to build as sub-projects of yours. Are you going to mention that at all? Like if there are any standard ways of doing it nowadays? Because it used to always be a bit hacky.
Yeah, exactly. Yeah, so we will cover this. There's a hands-on exercise of porting an old style external dependency to the modern way. Okay, then in CMake everything is organized around targets. So targets in the first examples were the executable and the library. So you had, for example, this my example executable, and you said target link libraries, and you linked another target into it, which was the library. And by this you can build a dependency graph where one thing depends on each other. So for example, this is from Google Test, the dependency graph of the samples that are there. So the basic of Google Test is the gtest library. Some executables, some samples directly depend on gtest. There's another library which is on top of gtest, so gtest links to this, and then these samples link to these libraries and implicitly to the gtest library. And then there are now a lot more commands how to deal with targets and how to build up these dependencies. And I will probably mention only the most important one. And we already know these. It has some options. So you can say if you build a library, it should be static or shared. add executable is clear. And then, as I mentioned earlier, there's the target links libraries, where you can say, for example, this executable links to some library that I created with add library. Then what you also might need is to tell some target where it can find its headers. And as you do with target include directories, so you tell which include directories should be used. And we will go into more detail how to do this properly. And you can specify on target also some compile definitions, compile options, and features. So this is about the C++ standard versions, for example. But we'll come to this all later. Now a summary of what we already saw. So the CMake build process split in 3 parts that you saw earlier. So the first is you call CMake . It will configure the project and will fill the CMake cache.txt with some information, for example, which compiler it detected and other options that you set manually. And from this cache, it will generate actually the make files. So typically on Linux, it will be make files, or for example, you can use this other generator for Ninja, you will get Ninja files. So configure, generate, and then here, this is what we get after calling CMake . So at this point, and then you do the actual building by calling make, and you get your binaries. Now in the configure process, you can specify different settings. And I will show this in another example. So first of all, if you just run CMake . It will fill all the variables that are available with some defaults. And you can check with CMake, so there's another C dot. You can see the values of these variables. So in my project here, by default, there are 2, and then there's my option that you saw earlier that I added manually. So the standard ones are CMake build type, so which kind of mode you want to build your project, either in release or in debug mode, or there are 2 other options which are not so relevant for now. And then there's a CMake install prefix, which is the default location where your stuff gets installed to. And this will be already there. Now what I can do is here, for example, I want to build my library in release. I set it here, and I want to turn this option, whatever it does, to off. So I just type enter. And now I need to reconfigure my project by typing C. And yeah, it did it already. And now it's configured. The CMake cache is filled with the new values. And then I type G and generate it. Now the thing is updated. And probably now it is building it in release because the unset CMake build type was pointing to debug. So that's why it rebuilt it. So CMake is a nice tool to change values, but you can also do this from the command line if you prefer this and you know the name of your variables. So here I can change the CMake build type back to debug. Then I can run make again, and now I have a debug build again. Now I was already referring to cached variables several times. So you saw in my example this option. So normal variables that you create with set, they are not cached. So when you run CMake, they are set to some value used and then later forgot. But if you make them cached, that means the values stay between invocations of CMake. So what you, for example, will do in one of the exercises, you can set the floating point precision to either float or double values, and this is something you want to store. You want to have it as an option available in CMake, and that's what you do with this cache option. And these cache options can have different types, so they are not really different in the sense that they are stored internally as different types, because internally all is strings. But this is how they show up in CMake or in the graphical CMake GUI. So if you set it to path, then you will get an option where you can click in the graphical user interface and open the file path. And option is just a shortcut basically for Boolean cached variables. All the variables that you create here will show up in CMake. Maybe some you don't want to show to the user because they are just internal. You can mark them as advanced, and they will not show there until you press a special command T. The CMake dependent option is already a bit more advanced. So a typical use case in our project is you have a library or an executable which you want to build with CUDA. And for CUDA, you have different standards for different GPUs. So the CUDA architecture. So now, usually we have an option that says enable CUDA. Now, if this is turned to off, you don't want to see the option to set the CUDA architecture. So then we create a dependent option that will only show if some other option is set to true. So if GPU is enabled, we will give this extra option. Now, apart from variables that you can set yourself, there are a long list of already built-in variables. One that I mentioned already, or that we saw already, is the CMake install prefix and the CMake build type. Then what you get after running CMake, it will detect a C++ compiler in our case, and you can get and you can set the C++ compiler also explicitly by changing this variable, setting it to a different compiler. For example, I don't know, now it detected GCC, I want to use Clang. I can change this variable and rerun, configure, and generate, and I get it compiled with Clang. I can also pass in here some flags for the language. So CMake CXX flags, I don't know, I don't have a good example because actually most of the time you don't want to use this thing. CMake module path, I will not explain it now. You will have to use it later in the hands-on. And then some other useful variables are variables that provide information about something. So with CMake current lister, you get the directory where your current CMake file is in. Sometimes useful. And the CMake current binary there will give you the directory where you're currently building. And then CMake also detects some environment variables. So if you don't want to change your compiler after running CMake for the first time, you can set, for example, the CXX environment variable to your compiler, run CMake, and in this case, it will detect this other compiler here because it will read the environment variable and write it here. Do you have time?
There's a clock on the desk there.
Ah, nice. Okay, good. So if you want to structure, like in any other programming language, your things, you can use functions. For example, if you have some operation that you want to apply several times, you group it into a function. And yeah, we will also have an exercise about this, where you, for example, the library that we're looking at has some tests. Now you want to build each individual tests, and you have to link the libraries to each of the tests. So you don't want to do it by hand for all the tests. You want to create a function which does this. And the syntax is explained here. So this defines a function. The first thing is the function name, and then there's the number of arguments. So arg0 is the first argument, arg1 is the third, and then you can even refer to any other arguments that are not explicitly listed here. So all the other arguments. So if you, okay, let's make an example. You have myf, and now I explicitly mentioned arg0 and arg1. Now if I pass in 3 arguments, then I can still get the value of the third one by using argn, which contains a list of all the rest. And you can also explicitly mention or refer to the additional arguments. So in this example, arg0 is explicit, arg1 is also explicit. And if I call it with fab, it will print this. And argn contains all the rest, cde. Or I can use this special variable, which is argv2, to refer to the third argument. Yeah, and as you hopefully expect, functions have their own scope, so all you do inside a function will not leak out to the outside world. There's another kind of function-like things. It's macros with same syntax, but these work as if you would copy the code exactly in this location as C++ macro, for example. And that's why usually you would want to use functions instead of macros, because they limit the scope. There's a special helper for functions, which is CMake parse arguments, which allows you to have named arguments. Oh, yeah. So, for example, I have here this function special install, and we could write it as just you pass a destination and a list of files. Like the first argument is the destination, and all the rest are a list of files. Now, if you have many options for this function, this gets confusing. So you can give them a name, destination, and the next thing is the actual destination. You can say files and a list of files. And here you have a keyword, if you like, that doesn't take any arguments. And this is the code that you need inside your function to use this feature. So what you actually do, you specify a function without any parameters, and you let this guy, the CMake parse arguments, analyze the input from here and give you the result in some variables. And you will have an exercise about this as well. I will skip over this. Now, the next big thing is where CMake helps a lot is when you have dependencies on some other packages. Because if you don't have some package managing functionality, what you would usually do, you need to find the include path and the library path and put it explicitly in your make file, whatever. Now, CMake offers the find package functionality. We say that we give the name and if you like some version number, like here, we are requiring boost. You specify the version number, you say boost is required, and since boost is a big package, we don't need all of boost in our example, we just require one component. And this will try to find boost. This is a built-in functionality in CMake. And then in your your executable, you just say, my executable depends on boost program options in this case, and it does all the rest. So it will pass you the correct include directory path here, and it will in the end link with this library. Now, how does CMake find boost? There are in general two modes. One is the so-called module mode, and this is what is used actually to find boost. Module mode is it is looking for a file called find package name.cmake. In the case of boost, this is provided by CMake itself, and this is just another CMake file which is very long in this case, and it tries some paths, some default paths on your system and so on, and provide all the necessary information that you can just do this simple link step here. And the other mode is config mode, and this is the recommended way if you provide your library. So what you do here is, when you install your library, you are providing a package name config.cmake file together with your library. And then you can point in CMake to the location where it can find this CMake module file, and all the setup is then done by the one who is installing the library. It's clear the difference? So basically, what we do in this module mode is something like CMake tries to find the library. And here in the config mode, you as the library developer say, hey, here's my library. And we have some exercises in session 2 and 3 about how to do this. Now the result after find package is called, you get a variable with the package name and found, so you can check if this succeeded or not. Okay, this is some advanced information. So sometimes I already mentioned in Boost, you don't require everything. For example, in the case of MPI, if you say find package MPI, you will get, I think, everything, including, for example, Fortran. But if you don't have a Fortran compiler, you will fail. If you just need C++, you should specify just CXX here. And this one, maybe I will mention later. I already said there, like find boost, there are many modules are already available by CMake. So if you use a common library, then the chance is good that you can just detect it with CMake, like find plus, find MPI, Python, and so on. And then there are some modules which actually don't look really for libraries, but they just provide some compile options. So OpenMP, for example, is built in your compiler. So what find OpenMP will give you is a target that has all the information that needs to be passed to the compiler to enable OpenMP. So for example, -f OpenMP will automatically show up in the build command. And now this is the last slide for this first session on how to install your library. And this is only basics, because we have a full session about installing your library. And this is not enough to do it properly, but good enough to get started. So after you defined your library with add library and all the rest, you want to install it. And there are two steps for installing a library. So one is to copy the compiled library itself. You do this with install targets, and you mention the target that you want to install, and you give a destination where it should put these files. And then you also need to install the public headers of your library by copying the headers also to some path. And here I'm using a helper, which is GNU install dirs, which derives from the CMake install prefix some standard paths. Like, for example, the CMake install libdir will be the prefix /lib64 on a 64-bit system. and the install dir will be CMake install prefix / include, and this can change on different operating systems. What default is here? Okay, this was probably a bit dry, but if you never used CMake before, somehow you need to get started. Do you have any questions so far? If not, we will start with hands-on.
I have one question.
Yes.
I often build.
Where is it?
Is there a trick to, once you build your CMake project, to move it to a different directory and it would still work? Because that works with any other build system.
No, CMake saves everything with full path. So
Yeah, that's.
If you're very careful, then you can move a build directory. Usually what you would do is you'd move a build directory somewhere else, and then you open the CMake cache file, and then you do a search and replace, and you can get away with that. But you also need to be careful that CMake stores some additional files in a subdirectory of the build directory, which is called CMake files. And then you also have to sometimes go in there. So what I normally do is I wipe the CMake files directory, search and replace in the cache file, and then reconfigure, and then, but it's not the recommended way, because
yeah, so I also wouldn't do it. I mean, if the cost of
what's the specific use case?
exactly, I would say
Someone
this.
cannot build his software, I build it under my user, and I want to gift it to the other user.
Yeah, but this is what does the user then do with that?
What CMake should fix that for you, because you'll have a CMake script, you'll run it, and it'll build, and then he'll run it, and it'll build, and all your problems will be solved.
It takes 8 hours to build, so we don't want to run it again. That's the reason.
I'm going to let Hannes take over.
Yeah, so I would say there's a problem in your setup at some point. If not your not that you created maybe, but someone created a mess, and now you're trying to work around it. I'd say.
Okay.
Yeah.
Just on that also, so if you or from my experience, most of the time, if you just set the install directory, so then you can build it somewhere, and then you have just the install directory to the correct place, and then most of the time it works.
Yeah. So what is the use case? I mean, because I still don't understand it. If you want to install it, then
I don't want to install it. I just want to build it.
yeah, what does it mean? Why do you want to build it and not install it?
And then,
Installing is just basically moving it after you built it.
Exactly.
yeah, that's right.
So if you want to install it, then CMake is your solution. If the other case could be that you want to build it and they need to also have the sources still available because they will develop with it, and then I think they should be smart enough to set it up themselves if they want to use it. So I think you want to install it most likely, and then CMake is the solution for you.
We'll talk about it.
But if it takes 8 hours to build, it will take more than 8 hours to move your project to CMake.
No, it moves much faster.
To CMake.
It's already CMake. It is already CMake.
Okay, and then let's discuss this in a break. Okay. Then let's start with some hands-on exercises. So we have some setup for you because we are using, as I said, the latest CMake. It's a very easy dependency, but it will still take time to download and install it probably. And so the first session will be over. So what we have for you is a setup of all things we need. So it's actually only a latest CMake and boost, just to play with it. So what you can do, if you have already access to Dint, then you can just go to Dint, clone this repository, and actually I asked John to introduce a fork. He didn't. So I expect that you already have your fork here, but probably he understood clone. Now you have a clone, it's also okay. But so what you would do here is git clone as John explained. And then there's an environment.sh in the root directory here, and you source it, and you will have the latest CMake available and also other things that you need. The structure of the repository is for this part of the lecture is in CMake hands-on. As I said, all examples are tested with the latest versions. So there are 4 folders in there with session 1 to 4, and each has a readme.md with the instructions on what to do.
Course login.
And if you don't have access to Dint, we have login for you. Each folder contains some setup, some CMake files, some C++ files as a starting point, and also the solution, which you probably should not look at them at the moment. We will discuss them afterwards. And I think in all the examples, you don't have to edit C++ files. All you have to do is edit CMake files. And maybe we can discuss some of your results. I don't know how it works out. We are doing this for the first time, as you know. So you could provide your solutions in a fork, because you cannot write to our repository. But if you fork the repository, you can put it into your fork. Do you know what fork is? If not, John will explain. OK, so this is the setup. And now all these exercises are around one library and an executable. The library is called .prod, calculates the dot product of 2 vectors. And an executable called .prodcl, which is a command line tool to calculate the dot product of random vectors. Very smart. So yeah, this is the basic setup. We just wanted to make some example that is not only called my example, but has something real, also not very useful. So in the first exercise, if you never use CMake, you probably want to do the most basic things. It's a very simple exercise. Compile a library and executable. Then there's an exercise to iterate over lists and write your own CMake functions. And the last exercise would be to link the library to the application. And at this point, we can have a look at the repository.